Hi, this is Ravichandra Reddy Duba. Today we are gonna take a look at Enterprise Data Lake and also on Apache Hadoop, how it helps Data Lake. Coming to the first slide, it's basic understanding of Data Lake and how it works. So think of Data Lake as an huge central pool where you can throw all your data, which is organized, semi-organized, or unorganized data. You can store it all for very low cost without deciding when or how to use it. And in traditional systems, you can save the data only after cleaning and fitting it. If something goes wrong, there is a chance of losing the data. So in Data Lake, we save the raw data first and only organize it when we pull it out to read it. This makes much faster and guarantees we never lose any data even if we don't know what's for it yet. And coming to the architecture, it has several layers. Data first comes in through the ingestion layer, which is like Frendo for real-time data streams and also for big data transfers. Then it lands into the storage layer, which is foundation built on HDFS. And above that, we have the processing layer, which is managed by Yarn, which acts as operating system for whole cluster. Then we have the access layer where people actually use the data for running reports or creating dashboards or complex AI models. So coming into the storage internals, HDFS works on master slave setup. The main node is the master in this. It does not actually hold the data, but it holds the map of where every data is located, keeping that map in memory so it can retrieve the data fast. The data nodes are the workers. They actually hold the file chunks on their local hard drives and constantly check in with the name node to prevent data loss. If a drive fails, we usually use replication policy. By default, every file chunk is saved three times in three different spots. Usually, we call it as rack awareness. So even though if any server is failed, we can retrieve the data from other server. Then if that fails, we have another option also. And coming to the storage optimization, for getting the fast data out, how we storage the files is also important. We usually start with simple record by record files like Avro, which is great for just bringing the data in, but for heavy reports, we switch it to Paraquet or ORC, which is columnar format. So this means it gives the if it gives the user data according to the query and neglects the rest of the part, which makes us efficient and fast. Coming to resource management, Jan, what you can think of is clusters, a control trafficker, and solve the big problem of sharing computer power fairly among different users and programs. Yarn acts as operating systems for entire data lake cluster. The resource manager is the main boss who decides which job gets how much computer power. Then the node manager is the local agent on each server responsible for launching and supervising the containers. And application master, which talks to the resource manager to request exact container it needs to run the task. And coming to the next slide, it's the processing layer. Apache Spark is a modern super fast engine that replaced older MapReduce format. Its use advantage is that it processes data in computer's memory across many steps, avoiding slow and constant writing to the disk that MapReduce has to do. We write our programs in data frames, which are like smart tables that allow Spark to use it, optimizer to figure out the absolute best and quickest way to run the job. This is possible because of lazy evaluation. Spark does not start working until we ask for a final result, giving the optimizer time to look at whole plan and cut out any as unnecessary steps before actual computing. Coming to data ingestion architecture, the way data enters into the lake depends on whether it's coming in slowly or in fast stream. For big one-time uploads from traditional databases. We use Scoop, which uses parallel job to speed up the transfer for real-time high-speed data like logs or website clicks. We use streaming tools. Flume is the example. It uses agents to collect, buffer, and save the stream to HDFS, making sure we don't create millions of tiny files that slow down everything. And more often, Kafka is used as highly durable, high-speed message highway that collects the data first, which then allows multiple systems, including Spark and Flume, to safely read the same stream. Coming to the low latency access, we have to remember that HDFS is great for reading massive files sequentially, but it's too slow for quickly looking up one single customer record. We need a system for fast operational lookups, and that is HBase, a NoSQL database that sits on top of HDFS. The HBase is designed for quick reads and writes. Its efficient writing speed is due to log structured merge trees architecture. Every write tree is first saved to log file for safety, then saved to memstore, and this allows for fast reads. And when memstore gets full, it's written out to an immutable file on HDFS, and a background process constantly merges these files to keep everything running quickly. And coming to the summary, the data lake gives us two fundamental wins. Technically, the separate design of HDFS for storage and YAN for power means we can swap out or upgrade any part, like moving to a newer version of Spark without needing to touch the data itself. This is truly flexible. And from business standpoint, the ultimate value is data democracy, the ability of anyone to store and use every piece of data, empowering data scientists to build powerful machine learning models on most complete and raw data sets, which is major advantage over competitors. Uh, and that would be all. Thank you for hearing me out.